March 18, 1940, era 8:47 hours. Hut 1, Bletchley Park, Buckinghamshire. The machine weighs 2 tons, steel, copper. 100 rotating drums connected by 10 miles of wire. 1 million soldered connections, each one a prayer that this insane contraption might actually work. Alan Turing stands before it, fingers stained with machine oil, a smudge of grease across his left cheek. The air in the hut tastes of metal and electricity, and the particular sourness of men who've been working through the night. Outside, March rain hammers the corrugated roof, a sound like distant machine gun fire. In his hand, a piece of paper. Intercepted German radio traffic. 26 characters. Random letters that represent an order to a U-boat pack somewhere in the North Atlantic. Instructions for where to hunt, where to kill, which convoy routes to target. The paper trembles slightly. Not from fear, Turing doesn't do fear in any conventional sense, but from the knowledge of what those 26 letters represent. Ships torpedoed, sailors drowning in freezing water, supplies that will never reach Britain, food, fuel, ammunition, the lifeline of a nation hanging by a thread in this 4th year of war. This machine, code-named Victory, though it's never won anything yet, is supposed to crack the Enigma cipher, the unbreakable code the Germans use for every military transmission. The cipher that's kept the Wehrmacht one step ahead for months while Britain bleeds out slowly in the Atlantic. Here's what the German naval commanders don't know. Standing on their bridge decks watching Allied merchant ships burn, the 27-year-old mathematician in this freezing Buckinghamshire hut has just reduced their 158 million possible encryption settings to something a machine can actually search. Here's what the British military establishment doesn't know. The strange, stammering professor who chains his tea mug to the radiator and cycles to work wearing a gas mask during hay fever season has built something that will reshape warfare forever. Here's what Turing himself doesn't know. He has exactly 14 years to live. That the nation he's about to save will destroy him for who he loves. That he'll die at 41 with cyanide in his blood and secrets still locked behind official classifications. Behind him, Harold Keane from the British Tabulating Machine Company waits for permission to throw the switch. The drums are aligned, the menu is plugged, the electrical contacts are hot. The question doesn't need to be asked. It hangs in the oil-scented air like smoke. Will it work? Turing nods. The machine begins to rotate. Alan Matheson Turing was born in Paddington, London, June 23, 1912. His parents, Julius, a civil servant posted to India, and Ethel, who preferred England, solved the problem of where to raise their son through a very British compromise. They didn't. Alan and his older brother John bounced between foster homes and boarding schools, learning early that being different meant being alone. The solitude suited him. Numbers didn't judge. Mathematics didn't care if you stammered or wore your shirt tucked in wrong, or forgot social conventions. By age 16, he'd taught himself Einstein's relativity theory from a book and spotted an error in the derivation. At King's College, Cambridge, he found his obsession, the limits of computation. Not computers, those didn't exist yet, but the theoretical question of what could and couldn't be calculated. In 1936, at 23, he published On Computable Numbers, a paper that would haunt computer science for the next century. In it, he described a hypothetical machine, a universal computing machine, that could theoretically solve any computable problem if you gave it the right instructions. Nobody understood what it meant. Not really. Not yet. What they understood was that Turing thought differently, saw patterns others missed, could hold entire logical sequences in his head while simultaneously forgetting to tie his shoelaces. He was brilliant and strange and utterly, catastrophically unmarketable for anything except the one job history was about to demand, breaking unbreakable codes. The Government Code and Cipher School, Britain's cryptanalysis centre, recruited him in 1938. Part-time at first, a consultancy. They gave him encrypted German police messages to examine. He solved them in his spare time, treating the puzzle like an abstract mathematical problem. Because to Turing, everything was an abstract mathematical problem. War, communication, intelligence, all just patterns waiting to be understood. There's a story from Cambridge that captures something essential about him. During his undergraduate years, Turing joined the Officer Training Corps, not out of patriotism or militarism, but because he wanted to learn marksmanship. He became a crack shot, treating bullet trajectories as geometry problems. When asked why he bothered, given his complete disinterest in actual military life, he said, "They might come in handy in a war." They were forecasting rain when Germany invaded Poland on September 1, 1939. 2 days later, Britain declared war. The day after that, September 4, 1939, Alan Turing reported to Bletchley Park for full-time duty. He carried a suitcase containing 2 books, a change of clothes, and a problem that had been occupying his mind since the previous summer: how to mechanize code breaking against a cipher system that changed its settings every 24 hours. He was uniquely qualified for this moment, not because he was the best mathematician at Cambridge, though he was, but because he alone understood that you could build machines to think. Not in the human sense, but in the sense that mattered. Machines could perform logical operations, could test hypotheses, could search through possibilities faster than human minds. What Turing possessed that others lacked was the ability to see mathematics not as abstract theory but as something you could engineer, could build with copper and wire and rotating drums, could use to crack a code designed by humans who believed their complexity made them unbeatable. He would prove them wrong. But first, he had to understand what made Enigma seem unbreakable. Atlantic Ocean, November 1939. The SS Athenia sank on September 3, 1939, the day Britain entered the war. A German U-boat torpedoed her without warning. 117 dead, including 28 Americans. It was the opening shot of what would become the Battle of the Atlantic. By December, the mathematics of Britain's survival are grimly simple. The island imports 2/3 of its food, all of its oil, most of its raw materials. Ships arrive from North America carrying the supplies that keep the population fed and the war machine running. German U-boats hunt those ships using coordinated wolfpack tactics, directed by encrypted Enigma transmissions that allow submarines to concentrate forces against convoys. In November 1939 alone, 41 Allied ships sunk, 72,125 tons of shipping lost. In December, 78 ships, 284,113 tons. The German submarine force is small, only 57 U-boats operational, but they're winning. Because they can read British naval codes while British intelligence can't read theirs. At Bletchley Park, in a Victorian mansion converted into Britain's cryptanalysis nerve centre, the problem is being dissected by some of the finest mathematical minds the country can assemble. The tactical problem is simple to state, impossible to solve. Decrypt German military communications in time to act on the intelligence. The Enigma machine looks like a typewriter. 3 rotors, later 4 for naval variants, each with 26 positions. A plug board with 10 cables, a reflector. You type a letter, and a lamp lights up showing the encrypted version. Type the same setup into another machine. Input the encrypted letter, and the original plaintext returns. Simple, elegant, unbreakable. The mathematics are obscene. With 3 rotors chosen from a set of 5, there are 60 possible wheel orders. Each rotor can start in any of 26 positions, 17,576 possible rotor settings. The plug board adds 150 trillion additional variations. Total possible daily keys: 158,962, 555,217, 826,360,000, 158 million variations. The Germans change the key every day at midnight. Every Wehrmacht unit, every U-boat, every Luftwaffe squadron, all using different keys, change daily, distributed through secure codebooks. Standard cryptanalysis is useless. You can't try every combination. If you tested 1 setting per second, it would take longer than the age of the universe to exhaust the possibilities. The rule preventing progress is written into the mathematics itself. Enigma's security comes from its combinatorial explosion. You cannot brute force search a space this large, not with humans, not with any imaginable machine. But there's a weakness, a small one, buried in the elegance of the design. Polish cryptanalysts Marian Rejewski, Jerzy Różycki, Henryk Zygalski found it first. In July 1939, just weeks before the invasion of Poland, they shared their methods with British and French intelligence in a desperate meeting near Warsaw. They'd been breaking Enigma since 1932 using a machine called a bomber, a device that exploited a quirk in how German operators transmitted messages. But in May 1940, the Germans changed their procedures. The Polish method stopped working. Time pressure is mounting through the autumn, the first winter of war. The sinkings continue. British naval intelligence can occasionally decrypt Luftwaffe messages. The Air Force is sloppy, reuses phrases, makes operational mistakes. But Kriegsmarine Enigma, the naval variant used by U-boats, remains impenetrable. Failed conventional approaches litter the project files. Hand analysis, too slow. Pattern recognition, insufficient when patterns change daily. Captured codebooks, useful when you get them, but dated within days and impossible to acquire consistently. What's needed is something that doesn't exist. A machine that can think through logical contradictions fast enough to narrow 158 million possibilities down to a manageable number before midnight, when the key changes and you have to start over. Gordon Welchman, a mathematician working parallel to Turing, understands the problem. We were trying to find a needle in a haystack the size of the universe. And the haystack changes shape every day. Turing's approach is different. He's not trying to search every setting. He's trying to eliminate impossible ones. The method depends on cribs, guessed plaintext. German operators are human. They make mistakes, use predictable phrases. Weather reports always contain wetter or wetter Vorhersage. Situation reports follow formats, and crucially, the Enigma has a fatal flaw. A letter never encrypts to itself. If you guess wetter appears in the ciphertext, you can eliminate any position where the encrypted letter matches the plaintext letter. The possibilities collapse. Not to one answer, but to a searchable number. But you still need a machine to do the searching, because humans can't test thousands of rotor positions per hour while simultaneously checking plugboard configurations. Turing's design, refined through late 1939, is conceptually simple. Wire together multiple artificial enigmas. Feed them the crib menu. Let electrical circuits detect logical contradictions. When the machine finds a setting that doesn't contradict itself, it stops. It's called the bombe, named after the Polish bomber, though Turing's version is completely different. More sophisticated, more powerful, more likely to actually work. The engineering falls to Harold Keane of the British Tabulating Machine Company. The specifications Turing provides are lunatic. 100 drums, synchronized rotation, electrical contacts that can survive continuous operation, all built to tolerances that didn't exist in commercial manufacturing. Keane builds it anyway, through the winter, while merchant ships sink, while the pressure mounts. While everyone at Bletchley understands that if this doesn't work, Britain might lose the war through simple starvation. By March 18, 1940, the first prototype is ready. Victory. They name it Victory because they're British, and irony is a coping mechanism. Nobody knows if it will work. The machine occupies most of Hut 1's floor space, 2 meters tall, 2 meters long, 1 meter wide. Bronze-colored panels. Someone will later call it a bronze goddess. Though to the engineers who maintain it, it looks like a metal bookcase having a seizure. Turing has been awake for 36 hours. This is normal. Sleep is an inefficiency. He drinks tea constantly, his chained mug a fixture after someone stole his last one, and eats irregularly, usually apple at bedtime, left half finished on his desk, while his mind works through another logical problem. The crib they're testing is from April 23rd. Captured German naval documents from a trawler seized by HMS Griffin provide the settings for that date. It's a proof of concept. Can the bomb find known settings faster than human analysis? The menu is already prepared. Dilly Knox and his team broke several messages by hand, identified the probable plaintext. Now they're feeding it to Victory to see if the machine can derive the rotor order and starting positions. The team is small: Turing, Welchman, Joan Clark, a Cambridge mathematics student who's proving herself sharper than half the men in Hut 8. A few engineers from BTM, the cryptanalysis section operating under conditions of secrecy so extreme that workers in different huts aren't allowed to discuss their tasks. Keane throws the switch at 0847 hours. The drums begin to rotate. The sound is distinctive, a mechanical clicking, rhythmic and relentless, like 1,000 typewriters synchronized. The electrical contacts sweep through rotor positions, testing each one against the logical constraints of the crib. The process should take about 20 minutes for a full run through all 17,576 three-letter rotor positions. If the menu is good, if the crib is accurate, the machine should stop when it detects a setting that doesn't contradict itself. If the menu is bad, or the crib is wrong, or Turing's logic contains a flaw, the machine will run forever and find nothing. Turing watches the drums rotate. His mind is already elsewhere, calculating improvements. The machine stops too often. False positives where multiple settings appear valid. They need more discrimination. Welchman has suggested something he calls a diagonal board, exploiting the reciprocal nature of Enigma's plugboard connections. The idea is elegant, brilliant. It would cut false stops dramatically. But that's for the next machine. Right now, Victory needs to prove the concept works. Minute 3, still running. Normal. Minute 7, still running. Expected. Minute 12, Clark checks the electrical connections. Everything's hot. The contacts are making. The logic is flowing through the wire. Minute 16, still running. Minute 19, a stop. The clicking ceases. The drums halt. Turing moves to the output panel, reading the electrical indicators. A rotor position, a potential answer. Clark pulls the indicated setting, begins the validation process, feeds it through a test enigma, checks against the known plaintext. Partial match, she says. 2 plugboard settings are wrong. This is acceptable, expected. The bomb doesn't solve everything. It narrows possibilities. Human cryptanalysts finish the work. 15 minutes later, after testing variations, they have it. The complete key for April 23, 1940. Rotor order 2v3. Starting positions QLA. Plugboard wiring. It's several weeks too late to actually decrypt April 23rd traffic in time to matter operationally. But that's not the point. The point is, it works. The machine can find a needle in a universe-sized haystack. Turing writes in his notes, Victory operational, requires refinement, speed inadequate for real-time application, but concept proven. His tone is clinical, detached. But the people in Hut 1 understand what just happened. They've mechanized intelligence analysis, turned logical deduction into an engineering problem, created something that can think, not like a human, but faster than any human could. The point of no return comes 3 days later, in a conversation between Turing and Commander Edward Travis, Deputy Director of GC&CS. How many of these machines would you need? Travis asks. Turing calculates. Different keys for different networks. Army, Navy, Air Force. Multiple machines per key to increase speed. Redundancy for maintenance. 50, Turing says, to cover the main networks. More if we're to keep pace with daily key changes. 50 machines, each costing thousands of pounds, each requiring maintenance, operators, space, electrical power. Can you make them better? Yes. Welchman's diagonal board will reduce false stops. We can improve the drum mechanisms, faster rotation, better electrical discrimination. Travis is silent for a moment. The institutional momentum is about to shift. The resources that would be required, the engineering capacity, The manufacturing priority, the personnel. Build them, Travis says. And that's it. The decision is made. The British government is about to industrialise code breaking, turn a theoretical concept into mass production, build an intelligence apparatus that will crack German military communications on an industrial scale. They don't know it yet, but they've just changed how wars will be fought forever. August 8, 1940. The second bomb, Agnes Day, quickly shortened to Agnes, arrives at Bletchley Park. It incorporates Welchman's diagonal board. The false stop rate drops by 90%. The effect is immediate, dramatic. Agnes can process a menu in under 20 minutes with minimal false positives. Suddenly, Luftwaffe Enigma traffic, the Air Force network, codenamed Red at Bletchley, becomes readable. Not every message, not instantly, but enough. By September, Hut 6 expects the day's red key to be broken by breakfast time. The sensory experience of the bomb bay is overwhelming. The machines multiply through 1941, 5 by June, 15 by December. Each one 2 tons of rotating drums and electrical contacts. The sound is industrial, mechanical, relentless. That distinctive clicking rhythm as the drums search through rotor positions. The smell of hot copper and machine oil and ozone from the electrical contacts. Women's Royal Naval Service personnel, Wrens, operate the machines on 8-hour shifts. The work is mind-numbing and crucial. Plug the menu boards, start the run, monitor for stops, record the output settings. Repeat. The rooms are dark, stuffy, hot from the machine's waste heat. The Wrens aren't told what the machines do, just how to run them. One Wren, interviewed decades later, remembers, "We called them the bronze goddesses. Horrible things, loud as factories. We'd come out of a shift deaf and dizzy. Didn't know until after the war we'd been cracking codes. Thought we were just running some kind of accounting machines." The enemy confusion is total. German military planners assume Enigma is secure. The mathematics are too complex, the key space too large. The daily key changes eliminate any possibility of cryptanalysis. This assumption is wired into their entire communications doctrine. They're wrong. Catastrophically wrong. May 1941. The Bismarck sortie. The German battleship slips into the Atlantic, threatening convoy routes. British naval intelligence intercepts Kriegsmarine transmissions. Hut 8, Turing's team, breaks the naval Enigma settings for May 25th. The decrypts reveal Bismarck's position, intentions, fuel status. HMS Rodney and HMS King George V intercept her. May 27th, Bismarck sunk. 2,200 German sailors dead. German Naval Command reviews the operation afterward. How did the British find them? Bad luck? Improved radar? Agents? They never considered their communications might be compromised. The unexpected chain reaction comes in March 1941. A German naval trawler, the Krebs, captured off Norway during the Lofoten raid. Among the seized documents, Kriegsmarine codebooks, complete keys for February, Bigram tables, indicator procedures. Suddenly, Hut 8 can read Naval Enigma. Not current traffic, the keys are a month old, but they can analyze the messages, refine Turing's statistical methods, understand the patterns German operators use. Turing develops a technique he calls Banburismus, a statistical attack using sequential messages to narrow possibilities. It works. Combined with the bombe, it makes Kriegsmarine Enigma readable. The effect on the Battle of the Atlantic is immediate. Starting in June 1941, Allied convoys can be routed around U-boat patrol lines. Not perfectly, not always, but enough. Shipping losses drop from over 300,000 tons per month to under 120,000. Lives saved, incalculable. Thousands of merchant sailors who don't drown in freezing water. Hundreds of ships that reach port with their cargo intact. The slow shift of strategic balance as Britain stops bleeding out through the Atlantic. Crew dialogue is sparse at Bletchley. The work is too classified for casual conversation. But there are moments. Joan Clark, working late in Hut 8, watching Turing stare at a failed decrypt. "It's not solvable," she asks. "Everything's solvable," Turing says. "Some things just take longer." A pause. "We're going to win," she says. Not a question, a statement. Mathematically? Turing considers. The Germans are operating on faulty assumptions about their cipher security. As long as they don't discover the flaw, their entire communications apparatus is transparent. So yes, we're going to win. He says it like he's describing a theorem. Certain, inevitable, already proven. Exhaustion is constant. The bombs run 24 hours. The cryptanalysts work in shifts. Messages pile up faster than they can be processed. German military traffic in 1942, 3,000, 5,000 intercepted messages per day. Near misses are frequent. February 1942, the Kriegsmarine introduces 4-rotor Enigma for U-boat traffic. Suddenly, naval communications go dark. The attack space explodes. Instead of 17,576 rotor positions, now there are 456,976. The existing 3-rotor bombs can't handle it. Shipping losses spike. March 1942, 273 ships sunk. April, 132 ships. The U-boats are winning again. Turing and Welchman design a 4-rotor bomb. More complex, more expensive, harder to build. The Americans, now in the war after Pearl Harbor, help. The US Navy's OP-20G and NCR Corporation in Dayton, Ohio, begin producing 4-rotor bombs at scale. December 1942. Allied cryptanalysts break the 4-rotor naval Enigma. The Atlantic battle shifts again. By mid-1943, U-boat losses exceed Allied shipping losses for the first time in the war. The luck factor is real but invisible to the Germans. Every pinch, every captured document, every seized ship with codebooks feeds the Bletchley machine. Every German operator error messages with Eins, 1, that Turing catalogues, predictable weather reports, repeated phrases, becomes a crib. The Germans are losing to their own operational sloppiness, amplified by British ingenuity. By late 1943, 211 bombs are operational across Britain. Outstations at Eastcote, Stanmore, Wavendon, Gayhurst. 2,000 Wrens operating them in shifts. The intelligence product, codenamed Ultra, flows to Allied commanders as sanitized reports. They can never say how they know, can never act too obviously on Enigma decrypts, or the Germans will realize their codes are broken. But they know. Rommel's supply lines in North Africa, German defensive positions before D-Day, U-boat patrol patterns in the Atlantic. They know everything. And the Germans keep transmitting, confident their Enigma machines are unbreakable. Oberkommando der Wehrmacht, Berlin, March 1943. Admiral Karl Dönitz stands before a map of the Atlantic. Red pins mark U-boat positions. Blue pins mark confirmed convoy sinkings. The pattern should be encouraging. His submarine fleet is growing, 400 U-boats now operational. But the losses are unsustainable. In March alone, 15 U-boats sunk. April, 15 more. May, 41 boats and 1,000 trained submariners lost in a single month. The British are anticipating his moves. Convoys change routes just before wolfpacks can intercept. Allied destroyers appear precisely where U-boats are concentrating. It's as if the enemy can read his mind. Dönitz orders a review of signal security. The report is conclusive. Enigma cannot be broken. The mathematics are impossible. The daily key changes ensure security. The investigation focuses instead on spies, on interrogated prisoners revealing information, on radar improvements. The possibility that their unbreakable cipher has been broken for 3 years never seriously enters their analysis, because breaking Enigma is mathematically impossible. They believe this with the certainty of men who've seen the calculations. 158 million combinations. Change daily. No computer capable of searching that space. No human team capable of hand analyzing it. What they don't know, Turing isn't searching the space. He's eliminating impossibilities using logic the Germans never considered vulnerable. Captured German documents after the war revealed the mythology they created about British success: superior radar, better sonar, luck, the courage of Allied convoy escorts, improved depth charges, better coordination between air and naval forces. All true, but missing the central fact: Britain was reading their mail. A Kriegsmarine signals officer, interrogated in late 1945 after Germany's surrender. We knew the British had good intelligence. We assumed it came from agents, from prisoner interrogations, from captured documents. The possibility that they had broken Enigma was discussed and dismissed multiple times. The mathematics made it impossible. The interrogator asks, "What would have changed if you'd known?" "Everything. Complete communications overhaul, different cipher systems, change procedures. We should have." He doesn't finish. There's nothing to say. The war is over. Germany lost. And one of the reasons, perhaps the central reason, is that they trusted their mathematics over empirical evidence. Post-action German reports from various campaigns tell the same story. After Bismarck, British located the battleship through unknown means. Possible agent reports from French ports. After convoy battles, enemy appears to have advanced intelligence of our patrol lines. Recommend investigation of security leaks in port communications. Security leaks, not cryptanalysis. Because cryptanalysis was impossible. The myth persists even after the war. When British intelligence finally declassifies some Enigma material in the 1970s, German veterans are shocked, disbelieving. Some refuse to accept it happened. One German signals officer, interviewed in 1978. "You're telling me that a mathematician and some machines broke our Enigma code for the entire war? I can't accept that. The implications are too vast. Every naval operation, every U-boat lost, all of it compromised?" The interviewer confirms it. Long silence. "Then we never had a chance," the officer says. "From 1941 onward, we were fighting blind against an enemy who could see everything we planned. How do you win a war like that?" You don't. The most devastating captured testimony comes from a German cryptographic specialist, interrogated in 1946. "We evaluated Enigma's security in 1942 after questions were raised about unusually accurate British intelligence. The mathematical analysis confirmed the system was secure. The combinatorial space was too large for any conceivable attack. We concluded the British had other intelligence sources. We were wrong. Fatally, completely wrong. But the mistake was logical, based on the mathematics as we understood them. We didn't imagine someone could engineer a machine to think through logical contradictions at the speed necessary to make the attack practical. That leap, from theoretical possibility to engineering reality, that's where we failed. Not in our mathematics, in our imagination." October 21st, 1941. Alan Turing writes a letter. Not to his superiors through the proper channels. He's tried that, been ignored, watched bureaucratic inertia strangle progress. This letter goes directly to Winston Churchill. Unprecedented. Probably career-ending. But necessary. The letter, co-signed by Gordon Welchman, Hugh Alexander, and Stuart Milner Barry, is carefully worded. It explains that the codebreakers have succeeded in breaking Enigma, that the intelligence product is crucial to the war effort, that they're being strangled by lack of resources, not enough staff, not enough bombs, delays in implementing solutions because the funding won't come through proper channels. The letter is hand-delivered to 10 Downing Street. Churchill's response comes within 24 hours. A single sentence scrawled across an action memo to his chief of staff. "Action this day. Make sure they have all they want on extreme priority, and report to me that this has been done." Fear of punishment for going outside the chain of command? None. Churchill understands what the bureaucrats don't. Bletchley Park is winning the war. The institutional response is immediate. Funding floods in. More bombs commissioned. Staff expanded. By 1943, 9,000 people work at Bletchley Park and its outstations. The operation grows from a Victorian mansion with a few dozen cryptanalysts to an industrial intelligence factory. How it changed doctrine, permanent. Before Bletchley, signals intelligence was a minor component of military planning. After Bletchley, SIGINT becomes central to modern warfare. The principle that communications can be intercepted, analyzed, and exploited reshapes military thinking forever. The Americans learn from British success. The National Security Agency, created in 1952, is directly descended from lessons learned at Bletchley. The entire modern intelligence apparatus of electronic surveillance, cryptanalysis, and signals exploitation traces its lineage to Turing's bombs. Post-war life for Turing is complex. The work at Bletchley remains classified. He can't discuss it, can't publish papers about it, can't claim credit for the most significant achievement of his life. He returns to Cambridge, then moves to Manchester to work on computer design. His vision for computing hasn't changed. He's still thinking about machines that can think. In 1950, he publishes Computing Machinery and Intelligence, proposing what becomes known as the Turing test, a method for determining if a machine can exhibit intelligent behavior indistinguishable from a human. He works on morphogenesis, mathematical biology, patterns in nature. Publishes groundbreaking work on how organisms develop their shapes, the mathematics of daisy petals, growth algorithms. It's brilliant and largely ignored in his lifetime. In January 1952, Turing's house is burgled. He reports it to the police. During the investigation, his relationship with a 19-year-old man, Arnold Murray, is discovered. Homosexuality is illegal in Britain, has been since 1885. The trial is brief. Turing doesn't contest the charges, doesn't lie. He's constitutionally incapable of pretending to be something he's not. March 31, 1952. Convicted of gross indecency. The sentence, chemical castration or imprisonment. He chooses the injections, diethylstilbestrol, synthetic estrogen. 12 months of hormone treatment designed to destroy his libido. The treatment renders him impotent. Causes gynecomastia, breast tissue growth, depression. The physical and psychological effects are devastating. He loses his security clearance, can't work on classified projects, can't travel to conferences in America, is monitored by police. Joan Clark, who he briefly proposed to during the war before admitting he was gay, visits him during this period. She'll later say, "He bore it with remarkable courage, kept working, kept thinking. But something in him was damaged, not his mind, his spirit." June 7, 1954. Turing's housekeeper finds him dead in bed, a half-eaten apple beside him. The coroner's inquest determines cyanide poisoning. Suicide is the official conclusion. Turing was 41. Whether it was suicide or an accident, he often conducted chemical experiments in his spare room, including electroplating work using potassium cyanide, remains debated. His nephew, Dermot Turing, believes it was accidental. Andrew Hodges, his biographer, thinks suicide is more likely given the surveillance and persecution he endured. The irony is crushing and obvious. The man who saved Britain is destroyed by Britain. The nation he helped preserve through brilliant mathematical insight repays him with chemical castration and criminal conviction for who he loved. The work remains classified until 1974. For 20 years, Turing's contribution to the war is a secret. The obituaries in 1954 mention his work on computers, his mathematical papers. Nothing about Enigma. Nothing about the Battle of the Atlantic. Nothing about the thousands of lives saved because he could see patterns in chaos. General Dwight Eisenhower, in July 1945, told the British intelligence chief that Ultra saved thousands of British and American lives and, in no small way, contributed to the speed with which the enemy was routed and eventually agreed to surrender. Some historians estimate Bletchley Park shortened the war by 2 years. Millions of lives. Millions of civilians who didn't starve during extended blockade. Millions of soldiers who didn't die in campaigns that would have dragged on through 1946 and 1947. Turing's specific contribution, Incalculable. The bomb was his design. The logical attack was his method. The vision of mechanized intelligence processing was his insight. In 2009, Prime Minister Gordon Brown issued a formal apology. On behalf of the British government and all those who live freely thanks to Alan's work, I am very proud to say, we're sorry. You deserved so much better. In 2013, Queen Elizabeth II granted Turing a posthumous royal pardon. In 2017, Turing's law pardoned thousands of other men convicted under the same laws. Too late. 60 years too late. The philosophical beat isn't hidden in platitudes. It's in the paper trail, the official documents, the calculated cruelty of a bureaucracy that punished genius for failing to conform. In Turing's personnel file, preserved in the National Archives, there's a letter from the Manchester Police, dated April 1952. It recommends denial of security clearance based on Turing's conviction. The language is clinical. Subject presents a security risk due to his sexual orientation and criminal conviction. Recommend termination of classified work authorization. The same file contains a memo from GCHQ, the successor to Bletchley Park. It notes that Turing had been offered $5,000 annually, a massive sum in 1952, to work on decrypting Soviet codes during the Cold War. The offer is withdrawn after his conviction. That's the cost. Not just a life ended at 41, but continued contributions prevented. Intelligence work halted. Computer science advances delayed. Mathematical insights lost. Because a man loved another man, and that was more threatening to the British state than letting German U-boats sink supply convoys. The final line of the coroner's report is clinical. Death by misadventure. Cyanide poisoning. Self-administered. Self-administered. As if that absolves anyone. In the Alan Turing building at Manchester University, there's a bronze statue of him, seated, contemplative, an apple in his hand, reference to his death, reference to his habit of eating apples before bed, reference to the Newton's apple that sparked insight about gravity. The inscription reads, Alan Turing, 1912-1954, founder of computer science, mathematician, logician, wartime codebreaker, victim of prejudice. It doesn't mention the bomb, doesn't detail how many lives he saved, doesn't explain that modern computing, modern intelligence analysis, modern cryptography all descend directly from work he did in a freezing hut in Buckinghamshire while Britain fought for survival. In Hut 11 at Bletchley Park, preserved now as a museum, there's a reconstructed bomb. Built over 5 years by a team of volunteers led by engineer John Harper, using original BTM drawings and the testimony of veterans who maintained the machines during the war. It works. The drums rotate with that same rhythmic clicking. The electrical contacts sweep through rotor positions. The machine can still break Enigma, 70 years after it would have mattered operationally. Visitors stand before it, reading the plaques explaining how it functioned. The mathematics, the logic, the engineering, the genius required to imagine that you could build a machine to think. What the plaques don't capture, can't capture, is the sound in that hut on March 18, 1940, when Victory's drums began to rotate. The smell of machine oil and electrical contacts. The tension of watching a 2-ton contraption search through mathematical space for a pattern that would unlock Germany's military communications. The moment when theory became engineering, when mathematics became machinery. When one man's insight into logic and computation changed how wars would be fought forever. The Germans called Enigma unbreakable. They were right about the mathematics, wrong about the humans who could imagine the impossible. In the end, the code that broke the Nazi war machine wasn't German. It wasn't military. It wasn't even intentional. It was simpler than that. More devastating. The Germans assumed their cipher was unbreakable because the numbers said it was impossible. They never considered that someone might build a machine that could think through impossibilities faster than humans ever could. Alan Turing looked at impossible and saw not yet solved. That distinction won the war. It also killed him. The bronze statue in Manchester shows him seated, thoughtful, an apple in his hand. The expression is calm, mathematical. Computing some problem only he can see. What it doesn't show, the trauma of the injections, the humiliation of surveillance, the genius slowly poisoned by his own government's fear of who he loved. What it doesn't show, the thousands of sailors who didn't drown because he could see patterns in chaos, the convoys that reached port because he taught machines to think, the war shortened by years because he understood that mathematics wasn't just theory. It was something you could build with copper and wire and rotating drums. History remembers the machine. It took 60 years to remember the man.